Hello, students. Have you ever thought about what the world is really made of? I mean, the really, really tiny parts? Well, today, we are going to be detectives. We're going on a journey to find out how scientists first looked inside the atom. It's a fantastic story, full of clues, surprises, and brilliant minds. So, let's begin. Okay, so first, let's quickly remember what we already know from our last class. We know that every atom has smaller particles inside it. We have the positive protons, and we have the negative electrons. And since the positive and negative charges are equal, the atom as a whole is electrically neutral. So far, so good, right? But this led to the big question, the main puzzle for scientists back then. Okay, so we have these positive and negative particles, but how are they arranged? Are they just mixed up together randomly, like fruits in a salad? Or is there a proper system inside? That is the mystery we are going to solve together today. So here is our plan for today's journey. First, we'll look at the first guess about the atom's structure. Then, we will study a very famous experiment that changed everything. After that, we'll see the problem with the new model that came from it. And finally, we'll see how another scientist solved that problem with a brilliant new idea. Let's get started. All right then, let's start at the very beginning. After the electron was discovered, a scientist named J.J. Thomson was the first to propose a proper model of what an atom might look like from the inside. So what Thomson imagined was this. He thought the atom was a sphere of positive charge. You can think of it like a ball of jelly or a watermelon. And inside this positive sphere, the negative electrons were stuck or embedded just like seeds are scattered inside a watermelon. This was famously called the plum pudding model. It was a good first idea, you see, because it explained why atoms are neutral. All the positive and negative stuff was mixed together. Now, Thomson's model was a very good starting point, but in science, we must always test our ideas. So another scientist, Ernest Rutherford, was very curious about this pudding model. He decided to design a clever experiment to check if it was actually correct. Let's try to picture this famous experiment. First, Rutherford used a source that shot out very fast, positively charged particles. These are called alpha particles. You can think of them as tiny, tiny bullets. Second, he aimed these bullets at a very, very thin sheet of gold foil. And when I say thin, I mean it was only about 1,000 atoms thick. It was almost transparent. And finally, to see where these particles went after hitting the foil, he placed a circular screen around it, which would glow whenever an alpha particle hit. Now, the results of this experiment were very, very surprising. The first thing they noticed was that most of the alpha particles, almost all of them, just went straight through the gold foil. They didn't change their direction at all. It was as if the foil was not even there. So what does this tell us? Let's think about it. If you throw a small ball at a solid wall, it will bounce back, isn't it? But if you throw it through an open window, it will go straight through. So the fact that most alpha particles passed through meant that the atom could not be a solid pudding. It had to be mostly empty space. This was a huge discovery. But that was not all. The second observation was also very interesting. They saw that a very small number of alpha particles did not go straight. As they passed through the foil, they were slightly deflected, meaning they were pushed off their path by a small angle. Okay, let's think like scientists. The alpha particles are positive. And what do we know about charges? Like charges repel. They push each other away. So for a positive alpha particle to be pushed aside, it must have come near something else that was also positive inside the atom. And because only a few particles were deflected, this positive charge must be concentrated in a very, very small space. But now for the most shocking result of all. This is the one that amazed everyone. Very rarely, about once in 12,000 times, an alpha particle would hit the foil and come straight back. It would bounce back completely, as if it had hit a solid wall. This was unbelievable. Rutherford himself was completely stunned. He later said that it was as incredible as if you fire a 15-inch shell at a piece of tissue paper and it comes back and hits you. Just imagine that. Firing a huge cannonball at a thin paper and having it bounce back. It was that surprising. So what could be so powerful inside an atom to make a fast alpha particle turn back? It had to be something very small, very dense, and positively charged. This led to the greatest conclusion of the experiment, that all the positive charge and almost all the mass of the atom is packed into a tiny dense center. Rutherford gave this center a name, the nucleus. So with these brilliant deductions, Rutherford proposed a brand new model for the atom. It was a huge improvement. But there was one big problem with it. a really serious flaw that classical physics could not explain. So, Rutherford's model looks something like this. 1. There's a tiny, dense, positive nucleus in the center. 2. Nearly all the mass of the atom is in that nucleus. And 3. The light, negative electrons are revolving around the nucleus in circular orbits, a bit like how the planets revolve around the sun. This solar system model is very nice to imagine, isn't it? But it has a very big problem. Think about it. The nucleus is positive and the electrons are negative. Opposites attract. So the nucleus is constantly pulling the electron towards it. What stops the electron from just spiraling inwards and crashing into the nucleus? You see, according to the laws of physics at that time, any charged particle moving in a circle should lose energy. It should radiate its energy away. So, an electron orbiting the nucleus should be losing energy all the time. As it loses energy, it would slow down and spiral closer and closer to the nucleus until crash. This should happen in a fraction of a second. If this was true, atoms would not be stable. But we know they are. This was a major puzzle. The model predicted that atoms should collapse, but they don't. The solution came from another great scientist, Niels Bohr. He took Rutherford's model and added one new revolutionary idea that made it all work. Bohr proposed something very bold. He said that electrons are not free to revolve in any orbit they want. No, he said they are only allowed to be in certain special fixed orbits. He called these special orbits discrete orbits or energy levels. A very good way to understand this is to think of a ladder. You can stand on the first rung of the ladder, or the second rung, or the third. But you cannot stand any empty space between the rungs, can you? Bohr said that these energy levels are just like the rungs of a ladder for an electron. It can exist in one level or another level, but never in between. And this leads to his second, very important point. Bohr stated that as long as an electron is in one of these special allowed orbits, it does not lose any energy. It simply does not radiate. It can keep revolving in that orbit forever, without slowing down and without spiraling into the nucleus. This single idea beautifully solved the problem of instability. It explained why atoms are stable. So, let's quickly summarize and see exactly why Bohr's model was such a big step forward. We'll just compare Rutherford's model and Bohr's model side by side to make it very clear. So you see the main difference? In Rutherford's model, the electron could be anywhere, which meant it should lose energy and crash. Think of it like a ramp. But in Bohr's model, the electrons can only be on fixed energy levels, like steps on a staircase. And on these special steps, they are stable and do not lose energy. This simple but brilliant idea explained why atoms exist at all and opened up a whole new way of looking at the world. And it all started with that simple question: what is inside an atom?